right, number of things to talk about today, including the fact that there is no class tomorrow. Friday is a faculty work day. I guess I knew this a month ago when I set up my office hours because I didn't list office hours for tomorrow, but it completely skipped my mind until a student reminded me of it, so you can thank one of your fellow students for having tomorrow off. So no class tomorrow, which means that I'm going to talk about homework 4 today. It's not due until a week from tomorrow, but normally I would talk about it on Friday. I'm going to talk about it today, even though I know a lot of people are still working on homework 3, but we'll get through the details of homework 4 today anyway. I also want to talk about the current ODP, and then I wanted to dig into fgets and sscanf, which will help you with the ODP and with homework 4. So any questions before we get into all of that? All right. Well, let's jump into it. So let's start off with the ODP 410. So ODP 410, this is another function. Okay, so you don't have to do input or output for this. That'll be a future one. So ODP 410, you're writing a function just like the increment function that you did for 410A. Your function is called pick. It takes a single argument, which is an integer, and it returns one of two things. If that integer is divisible by 5, you should return the number 1. If that integer is not divisible by 5, return that integer modulo 5. So basically, if your argument is n, return n mod 5, unless that's 0, in which case you should return 1. Okay, and not surprisingly, this is, you know, one of the pieces of homework 4, which will be your stick picking game written in C. So this function will be useful to you, okay, for your next homework assignment. You need to test this yourself, right? So write your own main program, your own test bed that calls pick with different values of an argument. You want some of those to be multiples of 5. You want some of them not to be multiples of 5. Okay, and then after you've done that, you know, call your pick function, see what the return value is, convince yourself that it works. Once you think your pick function is correct, link it to the test bed with this line, and then assess it like this. All right. Not a whole lot else to say about that, but any questions on that? All right, so let's take a look at homework 4. And there's a typo in the assignment as it appears on Canvas, and so I will fix that after class. And I'll show you the corrected version here. Alright, so homework 4. Homework 4 is the stick picking game, but written in C instead of bash. So everything that you've done as far as figuring out the algorithm for playing the game, looping through, alternating between user and computer turn and so on, all that's going to help you with doing homework 4. Okay? So the same basic behavior as homework 3, but there are some key differences, and you got to pay really close attention to these, okay, because these are all worth points. So key differences, well, probably the biggest difference, this is written in C, okay, otherwise it would be homework 3. So you got to write it in C, and it's got to run on the Linux server. That's where I'm going to test it. The user is always going to go first. So you don't ask who wants to go first, user or computer. Always the user goes first. Okay, that simplifies your code a little bit. The user may be really badly behaved. They might not type in integers. They might type in text. They might type in nothing at all and just hit enter. You need to handle all possible cases. Okay, your code should never under any circumstances blow up. It should never segfault. It should never abruptly exit. It should never go into an infinite loop. You got to be able to handle all the weirdness that comes with users. Okay, and we're going to talk about how to do that. Alright, when you start the game, there's two ways now to say how many sticks you want to play with. Okay, we got two possibilities here. And let me see if I can drudge up some code. Alright, I don't have code handy. I'll show you code on Monday. But basically there's two ways to start this game. So the first is to do this exactly like we did with homework 3. So the user can say stick and then hit enter. In which case the program should say, you know, how many sticks do you want to play with? And the user types in a number. Okay, that's just like homework 3. But there's a second possibility with homework 4, which is when you run the game, you can say stick, and on the same command line where you're typing the name of the program, you can specify a number. And if you do this, then when the game starts, it does not ask how many sticks, it just plays with 18 sticks. Alright, so two ways to specify how many sticks you're playing with. The usual way from homework 3, where you type the name of the program, hit enter, it asks how many sticks, person types in a number. But a second option where you type the name of the program, but before you hit enter, you type in the number of sticks that you want to play with on that same command line, and then you say enter. Okay, so this is what we called the other day a runtime argument, and this is what we called a command line argument. Right. So I said in first week of the course, I think, this is going to be an important distinction. Okay, in general, there's two ways to specify input to a program, runtime and command line. So runtime is while the program's running, that's homework 3. The new version for homework 4 is you can optionally specify a command line argument. Stick space some number, enter, don't ask how many sticks. That's how many sticks. Okay. Alright, if the person is going to tell you how many sticks on the command line, it's got to be just like this. Stick, space, and then how many sticks they want to play with. If they put extra arguments on here, that's an error. Tell them it's an error, game's over. Okay, so if they just say stick, that's legal. If they say stick followed by a number, that's legal. If they say stick followed by a number followed by other stuff, game over. Okay. Alright, however they specify the number of sticks, whether they do it on the command line or they do it while the program is running, you have to error check that number. It's got to be a legal integer, it's got to be at least 10. If it's not an integer, if it's haha, if it's a negative number, if it's less than 10, That's an error, print a message, game over. Okay? So any errors in choosing the initial number of sticks, print an error message, exit. So this is different from homework 3. Homework 3, they could try again and again and again to get an actual valid entry. Homework 4, bad number of sticks, game's over. Okay, just print a message. You don't know how to play, goodbye. Alright, once they've specified a valid number of sticks, the user is going to go first, and then the computer, and you're going to take turns. During the user's turn, they need to specify how many sticks they want. It's got to be an integer between 1 and 4. The thing I posted on Canvas said 3. That's a typo. I'll post that correction after class. They put in an integer. It's got to be a valid integer between 1 and 4. If they just hit enter, that's not a valid integer. If they say haha, that's not a valid integer. If they say -5 or 107, those are not valid integers. It's got to be an integer between 1 and 4. Okay, next difference from homework 3. If they put in a bad number, ask them again. If they put in a bad number, ask them again. Keep asking them. Keep trying until they make a valid entry. Don't kick them out after 2 tries. Don't kick them out after 200 tries. Keep asking. All right. So these are similar to what you did in homework 3, but fundamentally different. Right? Homework 3, they could specify the number of sticks as many times as they wanted, and they only got 2 tries to specify how many sticks to take. We flip that around here. They get exactly 1 try to say how many sticks they're going to play with. They get an unlimited number of tries to say how many sticks they want to take. Okay? The goal here is not that this is harder than what we did in homework 3. The goal is to get you practice in reading an assignment prompt and translating it into code, and then checking your code and making sure it conforms to the assignment. Okay? That's part of what we're trying to develop in this course. Alright. Most of today's lecture we're going to spend talking about how to get input from the user in C. And you're going to want to use a pair of functions, fgets and sscanf. Okay, we're going to spend most of the rest of the class talking about that. But if you use these 2 functions the way we're going to describe today and Monday, you should have no problem dealing with user input. If you try to use scanf as opposed to sscanf, you're going to have problems. If you try to use A to I, you're going to have problems. If you try to take the characters that the person typed in and convert them to an integer yourself, you're going to have problems. If you try to compare the first character they typed to 1, 2, 3, or 4, you're going to have problems. Okay? We're going to spend a lot of time talking about fgets and sscanf. And if you use those 2, you will have no problems. Right? Or you will have problems that we can help you with, and you'll get through them easily. Okay? But you got to use those 2 functions, and we'll see why today and Monday and over the coming classes. Okay, the one type of erroneous input that you're allowed to accept is if, for example, the person is asked how many sticks do you want to take, and they type in something like this. You can accept that as just a 3, and you can ignore this extra stuff after the space. That's legal. Okay, and I'm allowing that because if you're using fgets and sscanf, it's really easy to process input, assuming that you allow this to be legal. Okay, we'll tighten that up in a future assignment, but for now, if they say something like this, you can just take that as 3. If you want to be, you know, extra ambitious and detect this and say that's an invalid entry, that's okay. But I'm not going to test this case when I test your program. Alright, let's see, what else can I tell you? That's pretty much everything you need to know. Push it over to GitLab, homework 4 by 8 a.m. a week from tomorrow. Right, that's next Friday. Make sure it's named exactly uppercase HW004. Give me reporter access, and you're good to go. All right, we're going to go through enough C to let you get through most of this over the weekend. Okay, and then Monday we'll talk about processing command line arguments. But for today, I want to talk about runtime arguments. right? This case here, we'll deal with this case on Monday. Okay, command line arguments. If you know how to use argc, argv, you're good to go. Otherwise, I would say try to get your program done over the weekend, ignoring this one particular input option. Just assume the person's going to run the program like this, ask them how many sticks, and so on. We'll talk about reading in this input right now. That'll give you enough to finish this. You can get this done by Monday, okay? And then, you know, you don't have to worry about it next week. So that would be my suggestion, okay? And it's the same algorithm, the same, you know, nmod 5, all of that stuff from homework 3. So finish up homework 3, right? Make sure that's pushed over to get by 8 a.m. tomorrow morning. And then while that's fresh in your head, if you have time on the weekend, right, I would say try to knock out homework 4 as much as possible. All right, so any questions on homework 4 up to this point? All right, so let's talk about user input and about parsing. So in Bash, when we want to read input from the user, we just use the read statement. And read basically pulls in characters and saves them in a variable, and then we can just use that variable as if it's an integer. Okay? In C, it's a little more complicated. Okay? And this is going to be a big part of homework 4, right? Is all the stuff we just talked about making sure that the number of sticks is a legal integer, making sure that the number of sticks they want to take is a legal integer. So how do we do the equivalent thing in C? You've probably learned to use scanf as a way to read in, you know, an integer from the user and convert it into an int variable. Scanf is not your friend. Okay, scanf will get you into all kinds of trouble. Scanf, depending on what you're scanning into, has potential security issues. You can have buffer overflow vulnerabilities in your code if you use scanf just like gets. And so in general, we're never going to use scanf in this course. Okay, you'll never see me use it unless I'm giving you an example of why it can get you into trouble. When we deal with user input in C in this course, we're going to do the following. We're going to break the task of, say, reading in an integer into 2 pieces. Okay, so we're going to have 2 steps to, say, reading an integer in from the user. So step 1, read the user's input as characters and save those in memory. First thing we're going to do, we're just going to read the input from the user and save it somewhere. We're not going to interpret it. We're not going to say they typed a number 2, so this must be an integer that starts with a 2. We're just going to read what they type in, save it in memory. The reason being, once it's in memory, we can do whatever we want with that. We can interpret it 15 different ways. We can, you know, analyze character by character. We can run it through parsers and so on and so forth. First thing we're going to do, read the user's input and save it in memory as characters. And then, separate step, we're going to parse or interpret that saved input. And we're always going to try to break this into 2 separate steps. An ingest step, where all we're doing is grabbing the characters from the user and saving them. And then a parsing step, where we interpret that input. And for example, for homework 4, convert it into an integer. All right, we want to separate those steps. Scanf gloms both of these together into a single function call. Okay, we're going to split them out. So we're going to use two separate functions. Up here, when we do the read, we're going to use the function fgets. And to do the parsing, we're going to use sscanf. Alright, so ingest with fgets, interpret with sscanf. Alright, so let's play with fgets first. So we need to include standard io.h because that's where fgets lives, and it's also we're going to use some printfs. Make my main function. All right, so fgets, the goal of fgets is to read in input from the user and save it in memory. Okay, so we need to tell fgets where should we save the user's input, and we're going to save it in a character array. So we need a character array, so let's make that. So here's character buffer 120. This is just temporary storage for up to 120 characters of user input. You can name it whatever you want. You can make it as big as you want. But if I'm expecting the user to type in an integer, I should not make this, only 4 or 5 characters. Because they might type an integer like, 6 billion. And that's going to need 10 characters plus some extra stuff at the end. So make this big enough, right? Memory is cheap. So 120 characters, not a problem. Now, if they don't type in 120 characters, it's just extra space, right? But don't make this, like a small number, like 3 or 4. I would make this at least 20 or 30 characters. All right, so let's prompt the user. So we'll say, enter something. And I won't put my \n in my print statement, so this will print out enter something, colon, space, and it'll just sit there at the end of the line, blinking, waiting for the user to enter something. Okay, so that's called a prompt. That's asking the user to say something to us. Okay, let's read some input from the user. We're going to use the fgets method. Alright, so what is this? Buffer is where we want the user's input to be stored. 120 is the size of the storage available. Standard in we can take as meaning for now, read from the keyboard. It's not exactly what it means, but for now we can just think of standard in as a magic word that says read from the keyboard. We can read from files, we can read from the output of commands, we can read from network connections. Okay, for now we're going to say standard in, and we're going to take that to mean read from the keyboard. So this one function call is doing a number of things. It's saying I want to do some input. I want that input to come from the keyboard. I want you to read up to 120 characters, and I want you to store them in memory in this character array called buffer. Okay, and this is the way to read a line of characters from the user. Alright, an important note here, never use the function call gets. If you look at the manual page for gets, what does it say? never use this function. Okay? Gets is deprecated. It's in there for legacy reasons because there may still be some code that calls gets, and we don't want that code to break. Okay? But never use this function. Unless you're experimenting with security vulnerabilities. Then it's a really fun function to play with. Okay? Let's see. Question. For this assignment, do we need to handle if the second argument, pick2 haha, exceeds the buffer size we set up? So for command line arguments, we don't have to worry about buffer size because we're going to pick those up out of argv, and the space will be allocated by the shell. So the short answer is no. But we'll drill into that next week. All right. So don't use gets. The problem with gets is, what does gets say? It says read input from the user and save it at this chunk of memory, this character array that I've set up. But there's no way to tell gets how big that character array is. So you can run into what's called a buffer overrun. If you say gets, character array, the system will sit there and it will let the person type input in, and that input will get stored in memory in whatever array you've specified. But if you specified your array to be big enough to hold 120 characters, and the person types in 1500 characters, the gets function will store those 1500 characters in memory, starting with the location that you gave at the beginning of that character array. But after it's stored 120 characters, it doesn't know it's at the end of the array. It's just going to keep reading input in and storing it in memory. And depending on how your code is written, what happens after the end of that character array, who knows? Okay? It could be other variables. It could be flags. There could be a flag in there that says, is this user privileged? And by typing in the right things into this buffer, which maybe said, what is your name? You might be able to change the value of that flag. And now the code thinks you're a privileged user. Or you might be able to change executable code, depending on what kind of system you're running on. Or you might be able to change the return address on the stack so that when this function exits, instead of going back to where it's supposed to go, it goes somewhere else and maybe starts executing some system level code. Okay, so there's exploit potential in using gets. So we just have this general rule, never use gets. Right, and if you look at the manual page, it'll tell you all about it. But the basic problem is you can't specify to gets how much memory is available to store your information. Okay, now with fgets, that's not a problem, because fgets, we're telling it, we've only got 120 locations in here that you can use. So if the person types in more than 120 characters, it will only read the first 119 of those. It will store those in buffer. It'll store a null terminator in the 120th, and it'll return. And you simply won't have read the entire line that the person had typed in. And the next time you call fgets, you'll pick up the next chunk of stuff they typed, and so on. Alright? So don't ever use gets, like I say, unless you want to play around with vulnerabilities. Alright, so fgets will read input from the user, store it in this character array named buffer. So let's see what the user typed. So I'm just going to use a print statement. I'm going to print out the contents of that character array, right? So %s will get replaced with the characters in that array, and I'm going to print it out between angle brackets, just so we can see what was typed. And that's the end of our first piece of test code. So let's compile that, let's run it. I can say hello Nick, and it tells me user input equals HELLO space NICK, and apparently a new line character that got printed before the closing angle bracket. So that's one good thing to keep in mind. What the user types in and what you pick up with fgets seems to have a new line at the end. I can say hello, it's hello with a new line. I think I typed a backslash in the beginning. Alright, so there's hello. If I type just an enter, it says user input equals, and it's just an empty line with a new line in it. If I type a bunch of spaces and say haha, the input is a bunch of spaces followed by haha. If I put spaces at the end, those are in the buffer, but we don't see them, right? Because there's also a new line at the end, so we don't see the fact that some spaces got printed here, but they did get printed. And if I type in more than 120 characters, I should have just made my buffer smaller. If I type in more than 120 characters, it should read the first 120 of those into my character array, and then it should return at that point. What do you think? Have I got at least 120? Alright, so here my input was equal to all of this stuff. And there's no new line at the end, because it didn't get to the new line. It read the first 120, which got us down to about here. And it knew, hey, there's no more space to store things in our array, so it returned at that point. And now this is what our character array looked like. Alright, so this is super clean. Okay, this is just ingest characters from the user, save them in memory. And we want to do that first. Okay, just read data, store it in memory. So that's what fgets does for us. So now that we have the input saved, let's interpret it. This is where sscanf comes in. So sscanf takes 3 arguments. The first argument is the thing that contains the characters you want to interpret. Okay? Sscanf is a parser. It's a way to interpret characters as something else. So first argument to sscanf is the name of the character array. Second argument is like what we do with scanf. It's a formatting string. %d says I'm looking for an integer. Third argument is where we want to store the converted result, and this is where we have to do that funny ampersand. Okay, and we will definitely learn what that ampersand is about, and we'll demystify it. But for now, let's just be kind of mechanical about this. So buffer is the character array whose contents we are trying to interpret. %d means interpret as an integer. @I means store the converted value into variable I. Right? And I has got to be an integer because we're doing a %d, which means integer. Okay? The short explanation for what the ampersand is for, C uses what's called pass by value. If we just put an I in here, there's no way that this function can change the value of I. So we pass the address of I instead. And we're tricking the system into acting as if it was using pass by reference, or pass by address. Alright, for now, just always put the ampersand there. If you don't, you probably get a seg fault. Alright, so sscanf, 3 pieces. Thing that has the characters we want to interpret, a description of how we want to interpret it, in this case as an integer, and then the address of the variable into which it should store the interpreted value. Okay, let's do a print here. After calling sscanf I equals, let's print out the value of I. And someone asked in chat, any way to prevent that new line? No, but you can remove it. So when we talk about strings, we'll look at how we can remove it. But it's basically the last character in the array. You can check to see if that's a new line. And if it is, just change it to a null terminator. So we'll learn to do that later. All right, so here's a further piece of code to work with. So let's compile this, let's run it, enter something, I'll type the number 7. Okay, user input equals 7 with a new line after calling sscanf I equals 7. Hey, that's good, right? That's success. This is an integer, okay? Printing that 7 up here, well, that was just a string of characters. But down here, we've got a genuine integer. We can do arithmetic on it, we can, you know, increment it and decrement it and compare it to other integers and so on and so forth. So this is a big win here, right? The person typed in something and we change it into an integer. If the person types a bunch of spaces followed by a 7, we can convert that into an integer also. But if the person types something like, you know, seven, after calling sscanf I is equal to 0. And if we type ha ha ha, I is equal to 0. And if we just hit an enter, I is equal to 0. And if we type in a 0, I is equal to 0. So how do we know if the person typed in a valid integer or not? We can't just see if I is equal to 0, because 0 is a valid integer. Maybe they typed a 0, in which case, you know, I should be 0. Maybe they typed ha ha, in which case I is 0. But we need to know that something went wrong here, something went wrong here, something went wrong here. But this is valid, and this is valid. All right, so sscanf has a return value. Every function you call potentially has a return value. When I talk about the return value, I'm not talking about this. I'm saying we can take a variable and set it equal to sscanf. So let's do this. I'm going to do integer result equals sscanf. And let's take a look at the value of result. By the way, we're going back to VI on Monday or Tuesday, but since there's no class tomorrow, I wanted to get through this part of C today so that you can work on this over the next few days. All right, so sscanf returns an integer, which we're going to save in a variable called result, and we're just going to print that out here along with the value of I. All right, so let's run this. Let's put in an integer like 10. Okay, after calling sscanf I equals 10, result equals 1. When result is equal to 1, we know that the conversion succeeded. Enter something, -1, I is equal to -1, result is 1. If result is 1, we know the conversion succeeded. Alright, if I say ha ha, result is 0. Result is not 1, the conversion did not succeed. If I just hit an empty line, result is -1. Result is not 1, the conversion did not succeed. So here's your mantra. Alright, if the result is equal to 1, the conversion was successful. If the result is not equal to 1, the conversion failed. And this is important, okay? If you try to check to see if the result is 0 and say, well, it's not 0, it's exceeded, you're not going to get the right result. Success is 1, failure is different from 1. Right? But as we've seen, failure could be 0, it could be -1. Okay, success is 1, failure is different from 1. Alright, so question in chat, what if we have stuff after our input? So if my input is 10 and then some other stuff and then a 35, that's going to look like it succeeded. Okay, the number 10 gets stored in I, result is equal to 1. This is why there's that one exception in the rules for homework 4, where I say if there's extra stuff on the input, you can accept it. Okay, because it saves you from having to notice that there's extra stuff here and call an error. Alright, so why is result 1 when we succeed and different from 1 when we fail? Result is the number of things successfully converted. Okay, the return value from sscanf tells you how many things did sscanf convert. We are asking it to convert one thing. And if it succeeds in doing that, it will return a 1. That's why for this example, if result is equal to 1, the conversion was successful. If it's different from 1, the conversion failed. But if we called sscanf and we used a conversion format of %d space %f space %d, where we wanted 3 things converted, success would be measured by a result equal to 3, saying 3 things were successfully converted. And so if we needed all 3 things to be converted, we would say if result is equal to 3, we succeeded. If it's different from 3, we failed. So anytime you call sscanf, you need to capture that return value, right? Save it somewhere, like here where I'm saying result equals. And before you use these converted values, you got to check what that return value was. Suppose I said I equal to 123 before I call sscanf. Okay, well if I put in a valid integer, I is equal to that integer. If I put in something that's not a valid integer, I is unchanged. It was 123 before the call to scanf, it's 123 after the call to scanf. How do I know that 123 was the unchanged value as opposed to the person type in 123? Look at result. Is result 1? No. This was not a valid conversion. And I cannot go on and say the user must have typed in 123. Result is not 1. The person did not type in a valid integer. Pure and simple. It's that straightforward. All right. So this is everything you need to know to do like 90-95% of homework 4. Okay. The main trick on homework 4, I mean, you know how to do if statements, you know how to do loops, because you've done 121. The trickiest part of homework 4 is dealing with the input, right? And this is sufficient to do anything that you need as far as reading in how many sticks they want to play with, how many sticks they want to take each turn, okay? This will not deal with command line arguments, but Monday we'll talk about command line arguments, and it's really just using sscanf on argv and looking at argc. Okay, that's a separate topic. If you're coding this up over the weekend, ignore the possibility of a command line argument. Just run your program like you do homework 3. Ask the user how many sticks. Read in a number with fgets, convert it to an integer with sscanf. Check the return value, make sure it's equal to 1. If it is, this is how many sticks you want to play with. If it's anything other than 1, user error, game's over. Alright, questions on that? We're going to go through this a lot on Monday. We'll go into more detail, we'll go through more examples, and we'll add command line arguments. And I'll post this code over on the shared area on Canvas. but this should be enough to get you most of the way there. All right, so final comments on homework 4. You know, obviously start early, right? I'm a lot more available for help earlier in the week than later. In particular, I have office hours Monday and Wednesday next week. So start early. Modularize, break things into functions, right? ODP 410, that's a nice function for deciding how many sticks the computer should take. Code that into a function. It's already called pick, right? Put that into your file for your stick game, and when it's time for the computer to make a move, just, you know, number to take equals pick, parentheses, number left, right? And, you know, you can make a function for printing the number of sticks in the pile, for asking the user how many sticks to take, and that function can do all the error checking and so on and so forth. Throw that all inside a while loop, and you're pretty much there. All right, got a minute left. Any questions? All right, make sure you have your Git repository, whatever shape it's in, pushed over by 8 a.m. tomorrow. It'll get downloaded at 8 o'clock, and I'll grade it up Friday and over the weekend. I'll post comments. Do we have to separate the functions into individual files? You don't have to. For this point, I don't recommend it unless you know how to do that and you like doing it. I would make one file, stick.c, have separate functions in there, but it's easiest to have it all in one file. Eventually, we'll start working on breaking things into separate files and then putting them together, and that's where we'll talk about make files as a way to put the pieces together. But for now, easiest thing, one file. Nothing wrong with that at all. All right, cool. Have a great afternoon, have a good day tomorrow, and a great weekend, and I will see you on Monday. All right, thank you.